So chapter 6. So we're going to do chi-square tests. The first one we're going to do is goodness of fit. And goodness of fit is checking if the experimentally received distribution matches unexpected distribution. So we have some distribution of data, we're checking if it works. So goodness of fit is defined as a test whether a frequency distribution from sample fits. That's the basics of it. All right. So, how do we get it? Well, I'm going to put the steps over here so we can work with it. Step 1 is we're going to get the observed frequencies. Step 2 was we're going to look at the expected frequencies. Step 3, we're going to do the hypothesis test. And that comes with a bunch of subpoints. First one is first part is that the null hypothesis, the basis of the whole thing, is that the population frequency are equal to expected. Right, so we're going to assume the null hypothesis is true. Right, the null hypothesis, hey, population frequencies are what we expect. B. The alternative hypothesis, I'm going to say that the null hypothesis is false. Third thing is, well, when we do hypothesis testing, we need a very specific element. What's that specific element we need for hypothesis testing? We need a significance level, right? So we need some alpha. Yes. In a significance level. Since we are doing chi-square, we need degrees of freedom. And then E, the actual test statistic. Okay. And then F is the actual performing of the test. Okay. So this is the basics. Let's grab another black marker and see if we can keep on going. All right, so I'm going to try to do this with an example, and we can work through the example and see how this works. So, example. A survey So we have a survey of 1,600 coffee drinkers. So we run. Previous study gave the data, gave the following data. "72% of Americans drink coffee." At alpha equal to 0.03, is there enough evidence to conclude So we performed a survey of coffee drinkers, of 1,600 coffee drinkers, right? And we have the previous study gave the following data. 72% of Americans drink coffee. We're not surprised by this, right? Okay. At alpha or significance level of 0.05, is there enough evidence to conclude that the distributions are the same? And here is the data we collected. Wait, there's more. So the response N is this: 2 cups per week, 1 cup per week, 1 cup per day, and 2+ cups per day. Yeah, and we have the old study. The old study is percent of coffee drinkers. And we have 15%, 13%, 27%, and 45%. So the old study split up the coffee drinkers into the following categories. Perceivable that this could be old study. All right, the new study. And the new study had frequencies. The new study says I mean, this is how data is usually presented, right? Old studies, nobody shows you raw data, nobody gives you frequency, they give you percentages, right? They give you numbers, simple and easy to understand. 15% of coffee drinkers drink 2 cups a week. 45% of coffee drinkers drink 2+ cups a day. Is everybody comfortable reading this table? Yes? Maybe? Possibly? Okay. 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 So now we have this setup. Let's go through the steps. Right? Let's look at this. Population frequency is equal to expected. So we are saying, hey, this and this have the same distribution. That's the null hypothesis. So the null hypothesis right? This and this is the same distribution. So far, so good. Alpha 0.05. Degrees of freedom. No. Yes. But we're looking at a table, right? We're comparing if the old and the new data match up, right? Because to have the same frequencies, if I told you that if I tell you that on Tuesday I drink twice as many beers as I do on Wednesday, and I tell you, hey, I drank 4 beers on Tuesday, how many beers did I drink on Wednesday? Oh no, twice as much as on Wednesday. I would drink 2 beers on Wednesday, right? Twice as much on Tuesday than I do on Wednesday. So if I give you 1, right? So if I gave you this percentage, this percentage, this percentage, can you figure out the last percentage? Right? Which means that this is not a degree of freedom. So there's 4 choices, right? 4 categories. Only 3 of them are the degrees of freedom. So degrees of freedom are 4 minus 1. So you have 3 degrees of freedom. Okay. And now comes the test statistic. And for that, I'm going to do a little digression. When we're talking about chi-squared test statistics, we are looking at the following. You already met chi-squared. And we are looking at the sum of observed minus expected divided by expected. Right? We're looking at the value that we observed. We subtract what we are expecting from it. Then we have, right? We have how much the observed piece of data is away from the expected, and we divide by expected to put in the frame. Right? Or as most nodes will write it out is right. So So that's our test statistic. Okay. So we have the test statistics. So what comes next? Well, we run into a problem. You cannot put 15% and 206 in the same line. I'll give you a 5% raise, and I give you a 17-cent an hour raise. Are those two things comparable? What's the difference? Right, you need a base for the percentage. What's our base? Our base is this. Because hypothesis testing says, hey, this and this have the same distribution.
Oh, okay, so we have to divide.
So, what we're going to produce is we have to produce a table. I'm going to simplify it a little bit. So 2 cups a week, 1 cup a week, 1 cup a day, and 2+ cups a day. Right, that's my 4. Those are my 4 responses. Yes? Okay. Now, our percentages, so the old study, our percentages were 15%, 13%, 27%, and 45%. Now, because we claim, right here, hypothesis testing, we claim that this and this is pulled from the same distribution, right? That means that we would expect 15% of those coffee drinkers, right, to drink 2 cups a week. Yes? Everybody's with me on that. Okay, well that means that I have to do 0.15 times 1600. And this is 0.13 times 1600. And this is 0.27, maybe I should put an X here, times 1600. And this is 0.45 times 1600. Okay, so if this is our expected, this is our expected value, right? Because we are expecting this. So if this is our expected value, how much are those things? Well, if you multiply them out, we get 240, we get 193, we get 462, and we get 739.
That's 720.
Yes, sorry.
That one's 432.
432, yeah, sorry. Yep, I copied from the wrong column. I copied those. Right. 240, 208, 432.
432, 422.
Sorry? Oh, 432. You know what? Don't judge me. I'm dyslexic.
No judgments made.
No judging, just this is wrong. I'm like, no, just not your head.
Tell us we're wrong all the time.
No,
We are.
I don't tell you you're wrong. I walk around with a bell. Shame. Shame. So we have the expected value. Now, right, we can compare the new study to the old study. Right, we can compare what we observed to expected. Well, I'm going to slide this over, and we can make another column called the observed. I'm going to copy the right one this time around. Right, now we have a expected and observed. I just copied those from from the table. Sorry?
Okay, no, from the new.
Well, yeah, from our frequencies. Maybe I can be able to see. Yeah. Okay. So you can see this. So I got those numbers. All right. So what's next? Well, what we need? We need observed minus expected. So let's do observed minus expected. Observed minus expected. And we get minus 34, minus 15, 30, and 19. Observed minus expected. Observed minus expected. Where is it?
It always has to be observed minus.
Yes. The reason why is because it will keep you from making mistakes, even though we square it afterwards, right? So the difference is matters, not the sign. But I would still be careful, because once you start throwing out minuses, things go astray. All right. So observed minus expected squared, and this is 1156. 225, 900, and 361. It's getting big. And the last step, well, the last step is division by expected. So the last column is observed minus expected squared divided by expected, and we get 4.817, 1082, 2083, and 0.5014. Which means that the sum of observed minus expected squared divided by expected equals to, and I got the sum of this equals to 8.483. Okay, so we have a test statistic. Okay. So what do we know? Well, we know that we have a test statistic chi-squared equals at 8.483. We know that our degrees of freedom are equal to 4 minus 1, which is 3. We know that our alpha is at 0.05. So now if we look at the chi-square table, where is my chi-square table? Please tell me. Yes. So we're looking at alpha 0.05 and 3 degrees of freedom. What do we get? 7.815. Degrees of freedom of 3 and alpha, sorry, and not for alpha 0.5, the chi-square is right here. No, 7.815. Right? So we're saying that here this is those two things give us this number, and this number is 7.815. Where's our number going to end up? Our end up number is right here, 8.483. Which means what? Which means that, yep. Why? Yes. Because there's enough statistical evidence saying that, hey, those two aren't the same. We reject H sub 0. I'm going to cover the table for a second. Right? Our H sub 0 was the new data follows the pattern of the old data. Right? The population frequency is equal to the expected one. What is the expected? Well, expected is what we had before. We're expecting this. Right? The old study said this, we're expecting this. Which means that we collect some data and suddenly we go like, well, does this support this or doesn't it? Right? So we know that it doesn't. There's enough evidence. Now the more categories you have, the more degrees of freedom you have. The more degrees of freedom you have, the more the whole thing shifts down, the bigger the numbers become, right? It also means that the sum will grow. It's a fine balance. So, how many of you are thinking about doing accounting? Not anymore. Okay. How many of you are at some point going to work in public administration versus it's just a major? You know, I heard all the smart chicks take it. Sorry? Exactly, you're going to deal with numbers. So if I give you data, right, about patient sickness versus vaccination, and then you have a survey of it, like, hey, is this the same thing, or are we talking something different, right? So the first part of chi-square testing is exactly that, right? Are those two following the same distribution? Right? Another common one is how many gun owners voted for Hillary Clinton and how many gun owners voted for Trump. And then you run a survey and you're like, hey, is my survey following what we thought about this? Right? We started to do the cool stuff about statistics, and that's the cool stuff. Okay. Should we do one more, or should we try another topic? One more of those?
Yeah.
Yeah, whatever. All right, so an example. All right, there is, let's go with five departments. In a hospital. 5 departments in a hospital. A, B, C, D. And then we want to see if we're wondering if what? If the number of patients visiting each department is the same. Okay, so we have a hospital, we have 5 departments, we have patients. How many patients we're going to ask? We're going to say a survey of 1,100. Yeah. Just to be sure, we're going to ask everybody. Randomly selected. Patients. And my marker is dying again. Seriously, worse luck with markers today. Patients. And we're going to get the following data. So, department, A, B, C, D, and number of patients. And we have 262, 230, 34, 204, 190, and 200. What? Now you're ready. And we're going to do it at alpha equals 0.05. So the claim is that each department gets the same amount of patients.
Don't we already know it's not the same?
Why?
Because you say survey of, oh, I see it. Never mind.
Right? This is the problem. We don't do a census, we do a survey. Right? Yes, you could have, a survey that just asked more people coming out of the A department because there were more people coming. Right? You don't know if this is matching the population. Right? Well, so let's do the basics. Well, we're going to start with the null hypothesis. What is the null hypothesis?
Equal.
Exactly. Population frequency equals expected. Degrees of freedom.
One.
5 minus 1.
5 minus 1.
Can we just put 4 down instead of 5 minus 1?
Yes, but I'm putting 5 minus 1 just to, because there's one more, there's one of the chi-square tests relies on receiving data from the table, and when you start pulling statistics from the table to do an analysis, you lose a degree of freedom for every statistic you pull. So I'm doing this just so we are on track. But let's not worry about that. Let's do one question at a time. You know. Yeah. All right. So I'm going to cover this, and I'm going to start putting the big table on the main board so we don't run out of space. So this is so we had the department A, B, C, D, and E. What's the percent of patients? What is the status quo? What is the old way we're looking at? Okay, I'm going to show you the question again. What is the status quo when you look at this problem? Right, this is what we just got. This is new, fresh, off the press. Right, comes with bagel, cream cheese, and a coffee.
You
This-
have to convert that into percentage.
No,
That's observed, so you gotta find expected.
they're here. If the number of patients visiting each department is the same.
Oh, so you just divide it by the 5.
Well, no, so what the percentage of people? There's 5 departments. 100% of people go, 20%. Right? Okay, great. Well then, what's the expectations? Well, the expectations is this times the number of patients, right? And the number of patients was 1100. So 20% times 1100 is 22. Right? Oh, maybe I should do the first one by hand. So that's 20% times 1100, which comes out to be 220. And then all of them are 220. Right, what's the observed? Well, the observed is what we had in the table, and that was 262, 230, 34, 204, 190, and 210. Sorry?
You just say it's not true because the numbers don't match up at all.
Yeah, but they won't match up.
When you're looking for failure rate.
Sorry? No, so they won't match up because we are allowing ourselves a window, right, of significance. Say I want to set you up with my cousin. I'll tell you she is 5'6" and makes 45 grand a year. Okay, my cousin. You meet her and she's 5'7" and makes 52 grand a year.
Wow.
Will that make my statement about my cousin not true?
We're looking for
Well, if you're looking for very, yeah, exactly, but right, if I just ballpark it for you, like she's about 5'6" and makes about 40 grand, and she shows up and makes 52 grand and is about 5'7". Is the 52 away from 40 and the 5'7" away from 5'6" big enough for you to go like, that's not what I've been advertised, right?
Go by that standard, 5%, yes.
Well, right? On the other hand, if she shows up and she's 5.5 and makes 41, she's exactly as advertised, right? On the other hand, she can show up 6.4 or 6.7, and 20 grand a year. It's like, hell no, right? So this allows us for wiggle room because we are taking a sample. So some of those will be off. Like I tell you to flip a coin 50 times, are you going to get 25 heads? No, but if you get somewhere, let's say between 20 and 30 heads, that still looks like a reasonably good coin, right? You get 10 heads, it's like, oh, what's going on? All right, so we do this. So observe. So next one is what? O minus E, but not before C, right? What was that? That poker face with those shades gets me every time. So we have 42, 14, minus 16, minus 30, and minus 10. And we're going to go OE squared, and that's 764, 196, 256, 900, and 100. And the last column is O minus E squared divided by E, and that comes out to be 8.018, 0.891, 1.163, 4.091, and 0.455. And so chi squared, which is defined as O minus E, or the sum of O minus E squared divided by E, comes out to be, we're summing this up, we get 14,618. 14,618. Okay. My question is 14,618 too far? Well, we have to take this. We have to find our critical value. Sorry, we have to find our critical value. So let's look at the table. 5% and 4 degrees of freedom. Hmm? Again, the larger the test statistic is, the more evidence we have that the expected and observed things are different, right? So the more evidence we have that the null hypothesis is false. But having a large test statistics, right, and a significant level tells you where the cutoff is. So the bigger this number is, the more evidence we have that the statement of the population being as expected is false. So the larger this is, the more evidence that H sub 0 is false. But the larger DF, right, is, the more we allow ourselves space to be wrong. Because we have more categories to compare, right? The example with my cousin is the height and the paycheck, right? Where we say size of heels, number of cars, bedrooms in the house, right? Number of cats, right? I give you all of those, and she's mismatching on 3 out of 15, and all the other 12 are a match. There's a chance we just peeled a sample that is a little bit off, right? If we have a lot of categories, then the critical values get very large. But it also means that a lot of categories, that difference is going to add up. Because the difference gets squared, right, and divided, gets add up. So in this case, because that's a critical value, that's the statistic, we have evidence that those two aren't matching up, right? You had a claim, hey, all our departments are equally great, and you have evidence that, well, people prefer Department A a lot, and they really don't like Department D. And it's enough to make the statement that all departments are equally favored. The first time I learned this, I figured how many times my brother got pocket change from my parents and how many times I got it. And my parents like, you are all my favorites. I'm like, I has evidence. I did a chi-square. I'm not favorite. Like I'm feeling short-changed right here. Your statement is false.
Seems
Right?
like this is much easier than what we learned in chapter 5. No, I'm better at frequency tables than I am.
Well, okay, so this is all fun and games because the table is relatively easy. Like frequency distribution tables are easy. And again, everybody has a preference of a chapter that they're good at. But I show you chi-squared. This is the first time I introduce you to chi-square. You didn't have time to process it. And I show you, after doing Z tables, I show you this, like, hey, this is how you do this. Exactly, right? So I chose this to do this later. Some people do it somewhere in the middle of the semester. They do it, they introduce chi-square, and they're like, hey, by the way, right? And then comes hypothesis testing to standard deviations, and you're like in the middle of the desert. It's like, you know, Pakistan is 10 minutes this way, and you're like, what the hell did I sign up for? So this is this.